Today we're going to be proving congruence. Our learning target is I can show congruence by giving the sequence of rigid transformations that maps a figure onto another. So this is our last topic in Unit 1B. After this, we'll just be doing some review, getting ready for our test that is coming at the end of this week. So let's go ahead and get started. So first, confirming congruence. Two plane figures are congruent if and only if one can be obtained from the other by a sequence of rigid motions. So the only way that two objects are congruent is if there are a sequence of rigid motions that will map them perfectly on top of each other. If they don't map perfectly on top of each other, then it is not considered congruent. So if there's even just a tiny little bit off, it's not congruent. So the way that we do this is we map one figure onto another to prove congruence. Again, that's our main topic today. We want to prove congruence. These figures can only be mapped using rigid motions. So I can't use any dilations or anything like that. We can only use translations, rotations, and reflections to map these figures on top of each other. So if you ever see a dilation occurring, automatically know that they are not congruent because they're going to be different sizes. So we have these three figures here, figure 1, 2, and 3, and we're going to determine whether these figures are congruent or not. Now, the first thing that we need to be thinking about whenever we come across these shapes is if their orientation is the same direction, meaning that they're facing the same way. If they are facing different ways, such as figure 2, then we are going to use a rotation or reflection. If they are not facing different ways, if they're facing the same way, they have the same orientation, then we will use a translation, such as figure 1. So we should be thinking for the rotation or reflection in figure 2, think, does a reflection or rotation make better sense to land them on one another? So again, you guys should be able to look at this and consider, oh, if I rotate it, would it map better? Or if I reflect it, would it map better? That is how you're going to determine whether a rotation or a reflection works, based upon how it looks. So on top of that, we need to know which shape we're going from and which shape we're going to. So I went ahead and listed these out. And again, it's not always going to be this way. Sometimes I'd be going from E, F, G, H to A, B, C, D. It just depends. However, right now I'm going from A, B, C, D to E, F, G, H. Now important here, A must map onto E, B must map onto F, C must map onto G, and D must map onto H. So those pieces must go together. It's written in this order for a very specific reason to tell us which points correlate to one another. So they need to be written in order and they need to piece together well. So A has to go with E. A cannot go with G, for instance. So first goes with first, second with second, so on and so forth. Now, if I want to move A to E, they're facing the same way, so a translation works. So I need to move 1, 2, 3, 4 to the right, and then 1, 2, 3, 4 down. So if I follow the vector 4, negative 4, that should map A, B, C, D onto E, F, G, H. Now, for our second one, J, K, L, M goes to N, P, Q, R. So again, J goes with N, K goes with P, L goes with Q, and M goes with R. So, looking at these, would a reflection or a rotation work better in this sense? Well, in this way, a reflection would work better. If I reflect across, the orientation would make more sense. If I were just to rotate this figure, K would map onto Q. So K would map onto Q, but that's not supposed to happen. K must map onto P. So therefore, a reflection would work best. Now, if I need to find my line of reflection, of course, we can draw our line segments from pre-image to image, find the midpoints, and then draw a line through the midpoints. So we can still do that process in order to find our line of reflection. But in this case, our line of reflection is just going to be this line here. And again, I don't know the exact equation for this line because there's no axes to work from. So it'd just be this random line here. Same exact line as this one that's found through the two midpoints. Now, as for our last one, we see that they're different shapes. Sorry, not different shapes, but different sizes. And if they're different sizes, we automatically know that they're not congruent. Because if we have two figures that are congruent, they must be the same size. Everything must be the same if we're to say that they're congruent. So in this case, they're not. Now, you don't need to know this next part right now, but it will be useful down the road, especially once we get to semester 2. And that is how we can determine what our scale factor is, what we're multiplying by. So what I'm going to do is I'm going to find the length of ML. I'm going to find the length of ED. To do that, I can use either the distance formula or Pythagorean's theorem. I used Pythagorean's theorem, so a squared plus b squared equals c squared, and a squared plus b squared equals c squared. So ML is equal to radical 40, ED is equal to radical 10. From here, I do my pre-image over my image to find out what my scale factor is. So therefore, radical 40 over radical 10, that is equal to positive 2. So that means I'm multiplying by a scale factor of 2 to go from the small triangle to the large one. If I'm going the opposite direction, if I'm going from big to small, then it should be less than 1 or 1/2. I just put a 1 over the top of this. So, again, dilation, automatically know not congruent, but if I wanted to find that scale factor, we now know how we can. All right. So, use the definition of congruence to decide whether the two figures are congruent. Explain your answer. So go ahead and pause the video if you'd like and try this problem out on your own, and then we can go through it together whenever you're finished. All right, so with this one, looking at the first one, we notice that these two figures do not have the same orientation, so I can't use a translation. So what would be best to map these figures on top of each other? Well, if I want to map them on top of each other, the best way that we can do that is through a reflection. So if I were to reflect across a certain line, say the y-axis, then it should map perfectly on top of itself. So if figure CFED is reflected across the line x equals 0, also known as the y-axis, it will map perfectly onto JMLK. So the figure on the left, CFED, would map perfectly on top of this figure on the right if we were to reflect it over this line. Now the reason I know that, E is 1 unit away from our line of reflection, L is also 1 unit away from our line of reflection. F is 2 away, M is 2 away, C is 3 away, J is 3 away, and K is 4 away, D is 4 away, so K is 4 away. Now, as I was stating that, I just realized that my axes are going up by 2, so it's not actually 4 away, but this would be 8, this would be 2, this would be 6, and this would be 4. Because again, our axes are going up by 2, so the distance is doubled from what I was saying. So, as we can see, they all map perfectly because the distance is the same on either side of the line of reflection. Now, for our second one, letter B. Go ahead and pause the video if you'd like and try this one out as well. Looking at these, ABC and XYZ, these are not the same orientation. They do not have the same orientation. They're not facing the same way, so we must use a reflection or a rotation. For letter B, what would work better, a reflection or a rotation? Well, a rotation would. Just looking at the orientation, I can see that we're turning completely to the left. So, if I'm going from ABC to XYZ, I'm rotating in a counterclockwise rotation. Now, again, if we're going to be focusing on rotations, we're going to follow our rules, and we're going to be rotating about the origin. So when we list this, we need to be very specific. We need to have how much we're rotating, the direction, and the point that we're rotating around. So we're rotating around the origin, and if I want to find out how many degrees, well, I know that point Z is going to correspond to point C. So I can draw a line segment from my origin to point C and from my origin to point Z, and I can measure this angle here with a protractor. Well, what that angle is it's 90 degrees. So we rotated 90 degrees counterclockwise about the origin. So that's as specific as we can get. Whoops. We have how much we're rotating, the direction we're rotating in, and then lastly, the point that we're rotating around. So we have all three of those things, which is what you'll need. All right, let's go ahead and continue. Go ahead and pause the video if you'd like on this one, and then we can go through it together. All right, so looking at this one, it says the figures shown are congruent. So I already know ABC is going to be congruent to PQR. They already tell us that. It's written right above as well. Find a sequence of rigid motions that maps one figure to the other. So I'm going to map from ABC to PQR. Give coordinate notation for the transformations you use. So there's multiple ways to do this. If you get a different answer than me, that is okay. It's expected. If you get the same answer than me, awesome. You did it the same exact way as I did. So I'm going from ABC to PQR. So the first thing I'm going to do with ABC is I'm going to reflect it over my y-axis, which will give me this blue triangle here. Now my rule, of course, my coordinate notation, goes from xy to negative xy. The next thing I'm going to do is I'm going to reflect again, only this time I'm reflecting over the x-axis. So I reflect over the x-axis, all my y values now become positive, and I'm left with this purple triangle here. Again, my coordinate notation for this is x negative y. That's the rule for reflecting over the x-axis. Lastly, we're real close to triangle PQR, so it looks like I just need a translation because we're now facing the same direction. So I translate one unit to the right. So this gives me x plus 1 comma y. So this is my final answer. Now if I want to write it out in one single transformation, it's right down here. xy turns to negative x plus 1 comma negative y. Now again, that's not the only answer that works. Say I did a 180 degree rotation about the origin. And you may be wondering, don't you need to state the direction? Well, no, 180 degrees, it'll be the same regardless of if I go counterclockwise or clockwise. 180 degrees is just halfway around. So that would net me right to where my purple triangle is. And then from there, I would just do a rotation, or sorry, a translation. I just did a rotation. A translation along vector 1 comma 0. So again, that's another way that we can do this in 2 short steps. Just goes to show that this is not the only correct answer, but there's multiple correct answers in this as well. So keep that in mind. And of course, the rule for this would be xy goes to negative x negative y, which goes to x plus 1 comma y. And if I wanted to shorten it down, of course, xy turns to negative x plus 1 comma negative y. So again, lots of different ways that you guys can write this, but regardless, our final answer got us the same exact place. So keep that in mind. All right, let's go ahead and continue. You can go ahead and pause the video if you'd like and try this one out on your own for a second, and then we'll go through it together. All right, so looking at this one, again, same type of thing. I'm going from ABCD this time, ABCD to JKLM. So, looking at these, orientation is different. So I'm just going to go ahead and start by lining them up. So I'm going to go ahead and translate my figure along the vector -2, -10 to bring it down here. If they don't have the same orientation, I like to line them up so that I can have them become the same orientation. Now from here, since I did my translation exactly as I wanted it, now all I have to do is reflect over the y-axis. So if I reflect over the y-axis, I negate all my x values. So my x values become negative. And I now have my final rule, which is xy becomes negative x minus 2, y minus 10. Because as we can see, when this blue figure reflected over the y-axis, it turned into the green figure, which is the same as figure JKLM. So they map perfectly on top of each other. All right, let's go ahead and continue on. Here is our challenge question for the day. If you want to try this out in 2 steps, please do. go ahead and pause the video, try this one out, and then we'll continue together. This is our last problem of the day. All right, so if we were able to do this one, the first thing I want to do is, if we're doing this in 2 steps, I first need to line it up. So I'm going to go ahead and translate this figure, JKLM, along a vector so that it maps pretty well to WXYZ. Now again, they don't have the same orientation, so we're going to need to do a rotation or a reflection here. So I go ahead and I move it along the vector -4, -2. Now again, each box is worth 2 here. So -4, -2. And then at this point, well, I want to go ahead and map this perfectly on top of this other one. So what I can do is I can reflect over the line y equals -2. And if I do that, it should map perfectly on top, as this blue figure does, and we see that they are congruent. They map perfectly on top of each other. So therefore, our full rule should be xy turns to x minus 4, comma, -y minus 6. Now, again, I could have moved up and over and then reflected over the x-axis. I could have moved up further and over and reflected over the line y equals -2. Lots of different ways to go through this, again, but you should end up with the same final conclusion of getting there, and also this end rule should be the same regardless. All right, again, we were able to do it in 2 steps with just a translation and a reflection. But from here, we have now finished today's learning target. If you guys have any questions on this video, please let me know. Other than that, thank you guys so much for watching. I hope that you have a great rest of your day. Thank you.